Hello, welcome to TGIK. Thank God it's Kubernetes. I'm your host, Nadir Jiwa. I don't know why I'm trying to introduce myself as a TV presenter. So I'll be your host this evening, and today we're going to be joined by Jason. Hello, Jason.
Hey, great to be with you today, Nadir.
Cool. So we're going to be talking about Tinkerbell, which is a project part of the CNCF that manages bare metal infrastructure. Do you want to introduce yourself, Jason?
Yeah, so for folks that don't know me, my name is Jason DeTiberis. I've been involved in the Kubernetes community, specifically around cluster lifecycle management since about 2015 now, I think. I've been involved with the Cluster API project, formerly at Heptio, VMware, and now at Equinix Metal, helping to bring these cloud-native management ideas for Kubernetes clusters into the data center.
Cool. We'll just wait a few minutes for people to float in. So if you don't mind, if you can introduce yourselves in the chat, in the YouTube chat, and see who we've got. We've got Martin from the Netherlands. Hello there. Rory from Scotland. Was just there last week. Doing some biking. And nice to see you, Fabrizio. How you doing? Let's see. Right, so I'm just going to put a link to the notes as well. So go to the right place. And hopefully that works. Does YouTube even link? There we go. All right. Let's see what else. If you've got any ideas for news, we'll be covering what's happened in the cloud native community. So if you've got anything you've seen that's cool, maybe seen it on Hacker News, which I don't read, which I refuse to read. So if you've seen anything interesting there, throw that in the chat, and we'll get going in a few minutes. All right. Yeah, and just be aware I have closed the windows and the temperature is rising in my room. But it's either that or the noise is outside. So if I start looking a bit shiny, that's why. So just be aware. Got Yuraj, hello. How you doing?
It's a bit toasty over here too, Nadir, so don't be surprised if you see me start sweating too.
All right. All right, let's get started. So let's have a look at what's happened in the news. So the big news, I guess, this week or last week is the Kubernetes 1.22 beta is out. So got a couple of new features. And one thing to be especially aware of before you do anything else is there is a bunch of deprecated APIs. So if you are using things like admission registration or API extensions, stuff around CRDs, the beta APIs are going to be removed in 1.22. So make sure your applications are up to date. And one of the more interesting things that I saw this week was the interactive mode for exec credential providers. So a lot of people using kubectl with like SSO or external authenticators, and like got much better support for that today. So yeah, if you're working in a corporation or enterprise, that's really how you want to authenticate with your Kubernetes API server. So that's good to see. But yeah, please be aware of the deprecated API. So we also saw some sandbox projects arrive in the last 2 weeks. So I'm going to click on these. I haven't looked at a lot of these before, so we're just going to see what they're about. The first one we got is Kubella. So we've got had a quick look at this. It's using Q, which is a declarative configuration language, I believe, and it's around like helping you ship applications. So this is if you want a bit more layering on top of just shipping standard Kubernetes manifest, then this might be something you want to look at. So we've got that. We've got kubevip, which is something that we use actually. So be quite folk, and I think someone with Jason works on that.
Yeah, so kubevip is a project that's out there to specifically help folks that would need load balancers in environments where you don't already have a cloud provider there to provide the load balancer. So it's particularly helpful for on-premises type deployments, being able to support things like being able to migrate an IP using VRRP, or also using BGP and publish BGP announcements to provide load balancing services where you don't generally have it. It's similar to other projects in the space like Metal LB. It came out of Dan Finneran's the creator of it. He created it with some of the plunder work that he did a while back for prototyping on-premises Kubernetes deployments. And yeah, that's it. Compared to something like Metal LB, I think the difference is that there's a growing, more active community around kubevip than some of the things like Metal LB, where some of the issues have grown quite a bit stale, and trying to get fixes and changes in has become slow and problematic.
Yeah, that's cool. I mean, I hadn't even so we use it in vSphere primarily for the API server, the Kubernetes API server. So you're doing that at quite an early stage in the Kubernetes cluster lifecycle. So I haven't been paying attention to Kubernetes. I didn't realize we now support like a service type load balancer in Kubernetes. That's pretty exciting.
Yeah, and it's meant to do both of those things and be able to do both of those things in combination with each other and not fight with each other. In some cases, you can have issues with two different services trying to manage similar things like BGP routes between those two different use cases. And kubevip's designed to do both that API server load balancing and the service type load balancer.
Cool. All right, let's see what else we got. So we got kubedl, which is a deep learning project from Alibaba. I've never done deep learning. Don't know much about it. It's pretty cool, I suppose. And we've got two projects which I again not looked a lot at. They seem to be related. It's around service mesh and particularly around monitoring service mesh performance and the workloads underneath them. So it's all interesting to see. So move on unless anyone's got anything exciting in the chat. Just check. Hello, YMO. Sevi from Istanbul. Hi there. Yeah. Hi everyone. Hi Vlad. Cool. So today we're going to talk about Cluster API, and in particular, we're going to be talking about it in the context of bare metal. So we're not going to tread over old ground. We've talked about Cluster API quite a few times on TGIK, and you'll find links to the show notes. You'll find links to previous episodes in the show notes. Do not leave leave the live stream. Stick around. Don't go away. Look at them afterwards, please. So we're going to be looking at a project called Tinkerbell, which is what Jason works on. So I'll just get their website open. Do you want to just introduce what the project is about?
Before we go there, did we want to bring up the new release of Cluster API and the things that came along with that?
Thank you.
Yeah.
Keeping me honest there. So yes, Cluster API version 0.40 just got released this week. So, what am I doing? There we go. So this is the new V1 Alpha 4 release of Cluster API. So we've got big improvements to remediation of the control plane. So if you're not familiar with Cluster API, just briefly, Cluster API is a way of using Kubernetes to deploy and manage Kubernetes itself. We'll look into that a bit more. We'll have a look at it running a bit later on in the episode. But one of the things around rolling control planes is they're not like just replaceable throwaway items, right? They've got the data for the Kubernetes cluster. So we've done quite a lot of improvements, making sure that if something goes wrong, we're able to repair them. Machine health check was a way of like detecting problems with nodes and replacing them. And so there's been quite a lot more flexibility added to them. New thing that's been added is externally managed infrastructures. This is where you one of the things that the Cluster API providers do. So we have so there's different providers for AWS or Azure, and if you want to bring up a Kubernetes cluster in any of those environments, you're going to have to bring up some supporting infrastructure like networks, etc. These currently they stand up a sort of default template and sort of stamp out a sort of a usable set of resources that you want to use for your cluster, but you might want to use something else. So we've got improved support for where you maybe use Terraform or use some other cross-plane or AWS controllers Kubernetes to build out infrastructure, and then you can just tell Cluster API to use these bits of infrastructure instead and not to touch them, importantly. So do take a look. This is the core release, and some of the providers will be updating to V1 Alpha 4 as we go along. So take a look. It's not, you'll need to wait a little bit for the providers to be compatible with this version of the core release. Go play around, I suppose. Yes, so now back onto the topic that we are talking about today, which is Tinkerbell. Take it away, Jason.
Yeah, so the biggest question that most people have when we start talking about Tinkerbell is, what is it? And basically the goal of Tinkerbell is to provide declarative lifecycle management of hardware resources in the same way that Kubernetes allows for that declarative management of application services. So to do that, there's basically a few different microservice-based components that comprise that. The first one is the underlying Tinkerbell workflow engine. This is where you can define things like the actual hardware that you want to manage, as well as the set of actions that you want to perform on that hardware through the means of what we call templates, which is basically just a way of templating out a set of distinct actions that you want to perform on that hardware. A lot of the times we sit there and talk about Tinkerbell in the case of bare metal provisioning. It doesn't actually have to be provisioning operating systems on hosts. You can use it to run any type of set of orchestrated operations against your hardware using Tinkerbell. So that covers the templates, and then the last kind of component of the main Tinkerbell is workflows. And what a workflow is basically just a way to take a predefined template and apply it to a specific piece of hardware. And then once you have those defined, you have your hardware defined, you have some templates defined, and you have some workflows created. At that point, the other components come into play as well. So there is a boots component. This is the microservice that provides DHCP services, TFTP services, and basically is what performs the basic PXE booting environment for the hardware. And if folks aren't already familiar with bare metal management, PXE stands for Pre-Boot Execution Environment. And what we're basically talking about here is being able to have a DHCP environment that gives out an IP address to a host that isn't already pre-configured. From that point, depending on how the hardware is configured, it could try to do this PXE boot process in one of multiple ways. It could be legacy using the BootP protocol, which goes back many, many years to Windows-based network boot deployments. Or it could be trying to do one of the various different types of network booting in the various different types of hardware PXE implementations that there are. And that's going to depend, it could depend on what type of BIOS is installed on that host. It could depend on what type of network cards are installed on that host, all of that thing. Anybody who's had to manage infrastructure in a data center knows that there's very little consistency between different devices and how they support network booting as a concept. And because of that, one of the things that we do in boots is we do the initial network booting, and then we serve up over TFTP a standardized iPXE environment, which is basically just a small binary. And depending on, what type of host is talking to boots, if it's a UEFI one, it serves up a UEFI binary of iPXE. If it's a BIOS-based one, it serves up a compatible binary there. But it serves that over the network to the host, and then it really starts the standardized PXE boot process there. And from there, it decides, does this hardware exist in Tinkerbell? Yes or no? If the hardware does exist, is it configured to be able to do PXE booting? There's a setting in there. And if it is, then it also checks to see if there are any workflows defined. And if there are workflows defined, then it'll go ahead and offer up a small in-memory based operating system to the host. In the case of the example that we're going to use today, well, in the diagram up there, it's mentioned as OSI, which stands for Operating System Installation Environment. This was a larger initial OS image. And the idea is it's just an image that's meant to be able to bootstrap on any hardware and be able to run the Tink worker to be able to execute the workflows that are defined for the hardware. However, for the case of what we're talking about today, we're actually replacing that OSI image with an image called Hook. And this is another project within the Tinkerbell project. And it's an actual real minimal OS image based off of the Linux Kit project. And it's a much smaller OS image, whereas OSI was in the neighborhood of, I think, 2 gigs or so. The Hook image is down in a few hundred megabytes. So it can actually bootstrap into the workflows and start running the workflows quite a bit faster than the old OSI image would. In addition to that, there's also a metadata service called Heagle. And what that does is that gives us the ability to have cloud native bootstrapping workflows like you would have in a general cloud provider. You can have per system defined metadata that is available at runtime for use within systems like Cloud Init. So Heagle gives us the ability to actually use Cloud Init based bootstrapping, which when we get into the actual running of Cluster API provider Tinkerbell, we'll actually see that we bootstrap very similar to pretty much all the other providers using Cloud Init. There's also another component with Tinkerbell that we're not actually going to be using today, and that one's called PB&J, which stands for Power Boot in Jelly. I don't think we ever defined what that J really stands for other than jelly, because how can you have PB without jelly? But this component actually provides interaction with BMC management components. So you can actually do things like power on systems remotely and things like that, where if you don't have that component, which if we get to my local lab environment here, I don't have any fancy hardware, so I actually have to go and physically turn buttons on and off. And if you're in a data center, you don't actually want to force somebody to do that. So with PB&J, you can interact with the baseman management capabilities in server class hardware and be able to remote power on and power off systems and interact with them a little bit better.
Cool, thanks. So in our sort of standard TGI format, we normally just download the repo live. Decided at that point, given that we're dealing with bare metal and we need some hardware, we decided that's probably not going to be the best approach. So I'll go through. We've got two lab environments. Got Jason's, which is going to be a bunch of NUCs, I believe, some Intel NUCs. Got mine. So I don't have a bunch of free bare metal. So I did these actually using VMs because there's no reason why you can't. As I said earlier, there's no reason why you can't use Tinkerbell to deploy to VMs. So I'll just show you what my lab looks like, which is like this. Yeah. So yeah, this is super. I am available for my rates are competitive if you need me to do any cabling. So yeah, there we go. So I live in a flat in London, be aware. So don't have a lot of space. So this is basically in a cupboard, dryer cupboard, which has got my sort of mechanical heat recovery ventilation unit. There's like an iron next to it and a bunch of like face masks and other random junk. So that's where that lives. So I've got 3 desktops. They're Core i5s. They do have BMC in the form of Intel Repro, but they're all consumer grade. It's pretty much all consumer grade hardware. Otherwise, so I think one's Core i7 because I bought a newer, 2 Core i5 machines. They've got one. They've all got Intel 10 gig card, and then that's connected to this switch here. And then we've got 1 gigabit networking for the VM network. So if you're not familiar, vSphere has a replicated file storage, not file storage, replicated block storage technology called vSAN. So you need some fast networking for that. And then remotion is the ability to move VMs between different machines. So you need to copy the memory in as quickly as possible. So that's what that is. And then on top of that, I've got so this is what the vSphere environment looks like. So we've got our 3 hosts, server 3, server 4, and server 5. Don't ask me what happened to 1, 2, 3. So what I've done here is I've created a folder in vSphere. It's not really anything more than just a way to organize things, the file hierarchy, not much more than that. I've got one machine which is going to run the Tinkerbell environment and Cluster API. Oh, make that bigger. And we've got a bunch of machines which are going to act as the bare metal. So we've got basic machine 0, 1 to 4. They are powered on. They're just on. They just keep cycling, waiting for DHCP information. So they're set up to boot from the network. They're set up as UEFI, and they're currently rebooting every 10 seconds because there's nothing's offering anything to them. This is all sitting on its own VLAN. So each of these hosts have a virtual switch. So we created a Tinkerbell VLAN, VLAN 103. And then we've configured that in. So I use a MikroTik switch. So we've got a VLAN here, VLAN 103. We've connected that to the 3 servers and the switch itself. Given the switch an IP address for routing. So that's going to live at 192.168.103.1. And one thing we'll get into a bit later is we've added a route into the core switch table to point 169.254.169.254 at the sandbox VM. which is living on point 2. So if you're not familiar with 169.254, 169.254, that is normally the AWS IMDS endpoint. So if you're doing anything in AWS, and every virtual machine in AWS has a 169.254, 169.254 endpoint that you can contact to get metadata about yourself, which Tinkerbell is here doing that in the form of Heagle, which we'll go through later. So this network is fully isolated apart from having a router in it. And so there's no conflict with my wireless network or anything like that. And then what we've used is the Tinkerbell sandbox. Now, I didn't need to use VMware at all, as I found out later. Well, when I noticed, you can use Vagrant with it for this, right, Jason?
Yeah, so we wanted to try to make the sandbox as approachable to people as possible. So there's 2 options in the sandbox right now. There's the Vagrant-based environment that will basically spin up a minimal system so that you can have a provisioner VM and at least 1 worker VM. I think you can specify some number of worker VMs as well. But that's basically a way to kick the tires without any type of hardware investment. There's also a Terraform-based one that lets you spin up an environment using actual Equinix Metal hardware as well. And I'm sure you used the bare Docker Compose-based workflow when you were standing up your environment. So if you do have the hardware or VMs available, you can go that route too.
Yeah. So we'll just go through some of that now. So what? Is that the right thing? No, that's yours. That's mine. That's mine. There we go. Right. So started off with the sandbox environment, and I ran this script, which I believe fiddled with my networking a bit on my machine. Is that right? So it created. Did it set up some IP tables rules with my connected Docker or something?
It did. It's mainly was intended for using within the Vagrant environment, so that you're starting with a machine that's not already pre-configured with the IP addresses, so it's trying to set that up for you. I think if it hasn't already landed, there's work being done to make it more easy to run without overriding the network settings on the local host, because as you saw, it can be problematic at times.
Yeah. So and we just take a look at. So I'm not a regular Ubuntu user, folks. So I'm normally Fedora. So I believe there's a file in here. That's right. Let's have a look. So ENS 192, which is the network interface. So we added the 169.254, 169.254/16. So this is where this machine is going to pretend to be a IMDS service, and we'll go into what it's doing, how does Heagle, how does this actually work in a bit. But yeah, that's that, and we have some rules in the NAT table. Ooh, no, spell that wrong. It's lowercase. So yeah, we've got some NAT rules that will pass ports on this VM to Docker. So this got Postgres port, HTTP port, and that. So we'll go through some of those components as well. So the other important thing is in this sandbox. Oops, no, let's get out of that. So we have this deployed. First of all, we've got this env file. So you run this generate env that with some stuff, and it creates a it originally would download OC, and then but we will replace the I have already replaced the hook in a minute. So it downloads the Tinkerbell components from key. Is it key? It's key. This the host IP, and then it's got some usernames, passwords that it generates. And finally, you can see my administrative password for the vSphere. I will rotate this afterwards. Didn't know about this beforehand, don't worry. It's not a regular password that I'm using. And you go, it's not on the internet, so you can't log in. Don't try. Okay. Right. So, and then in the deploy directory, we have some stuff set up in the state. Let's have a look at that state directory. So, so it created some certificates for us. Is that right, Jason?
Yeah, so it's going to go ahead and create some certificates. It's also going to do things like set up the some of the state that we need, persistent state that we need for some of the prerequisite services. So in addition to the services we talked about, there's a Postgres database that's a dependency. There's a web server, and there's a OCI compliant registry that's needed. So the state directory actually stores that. And if you're running it on the Vagrant environment, it actually mounts those directories into the Vagrant environment. So if you're tearing down the Vagrant environment, bringing it back up, it comes back up quicker the next time because it saved the previous state from the last run. So you don't have to do things like download the OC or hook image and get that in place on the web server again. You don't have to reload any images that you've loaded into the OCI registry for running the actions. And you don't have to regenerate new TLS certificates for the purposes of talking to Tinkerbell and that sort of thing.
Cool. So this web root folder contains the directory that's going to be served up by Nginx, and in that I've got this tinkymaster.tar.gz, which is actually from the Hook project. I'm not going to build it because it takes quite a while. So it was a bit fiddly as well. So that expands a init RAM FS and a VM Linux. Do you want to just explain what those are for folk who are not familiar with those items?
Yeah. So you have two different files here. The first one is the actual kernel binary, and then the second one is going to be an initial RAM disk that can boot up for the OS. And since we're not talking about an OS that's being installed on the disk, there is no root file system. So everything runs in that initial RAM disk in kind of a ephemeral state.
Cool. And the final thing we've got here is Ubuntu 2004 kube v119.11.gz. So that's been built from, where's my browser gone? The image builder project. So this is used for most stuff in Cluster API. So with Cluster API, we are creating machines from disk images that have all the bits pre-installed. We don't want to be, because in most cases you want to scale quickly. You don't want to spend time installing all of the components when you boot up. So we rely on pre-generated images, and there is a recipe for building a raw image for use with Tinkerbell. That's another thing I ran beforehand because it uses QEMU, and my environment is virtualized. So nested virtualization is somewhat slower. So I did not do that again. Yeah, sorry.
Yeah, it could definitely take a little bit. The other thing too is this was our second iteration for the Tinkerbell provider. The first one did, like you said, we downloaded all the bits at runtime, and it gets fiddly because sometimes a binary is just not available. You know, there's internet routing issues, or sometimes some packets are dropped here or there. So you end up with inconsistency, or you may end up with completely different binaries if you're doing things like updating the system packages when it comes up and things like that. So Image Builder allows us to do that. However, in a future iteration, you will not actually have to copy the Image Builder based image to the web server or a web server. You can now with Tinkerbell, you can stream an image directly from an OCI compliant registry as well. So we're going to be looking at how do we update Image Builder to be able to publish to an OCI compliant registry, and then updating the Tinkerbell provider so that it can pull the image directly from a registry. That way, we'll be able to offer a better experience similar to what you have with like the AWS provider, where you can get a kind of default upstream pre-built image to use, and you wouldn't necessarily have to do the image builder based thing. Even though if you're talking about a production environment, you should probably be building and validating your own images anyway.
Yeah, that sounds super cool. I think another thing you could do that would be interesting is not to have to start a VM to build the image, given that this is kind of like a flat file system. So it's not, could potentially build it in a Docker file or something like that to produce the image and remove that one layer of steps that we currently do in image build. So if you're not familiar with image builder, we're generally always creating a VM, whether that's on AWS or Azure or on a VMware or whatever, to build the image. But there's nothing, given that really we're interested in files in a particular place on a file system, we could not do that even.
Yeah, we explored potentially a few different ways. Like we have an actual image builder similar process for Tinkerbell in general for folks that aren't using Cluster API. And I believe that's called Crocodile, because why not keep the Tinkerbell references going? And you can build everything from an ESXi image to a Windows image to a Linux image, and stream it to and from an OCI compliant registry. However, for the purposes of Cluster API, we wanted to try to maintain as much consistency with upstream as possible. So even though we could optimize some of those things, we saw more value in trying to do the same things with Image Builder that the other projects are doing, just for that consistency and ensuring that you have that similar experience.
Cool. And that, I didn't actually take a look at that. So that GZ file, is that a raw disk image?
Yeah, that's basically all that is. It's just a gzipped, raw disk image. It'll eventually get written to disk just with DD.
Okay, cool. Yeah, so those are the bits. So given that I did do this before, so what I played with this before, so kind of reset the environment. I'll just talk you through the things that I did to reset this environment. So it's today, this sandbox repo hosts the Tinkerbell components using Docker Compose. And I did see a repo that's moving it to a Kubernetes deployment. But I was a bit too afraid to try that just yet.
Yeah, well, internally within Equinix Metal, we run Tinkerbell and basically all of our management stack on top of Kubernetes. So for our purposes, having a first-class Kubernetes deployment for Tinkerbell that works out of the box is beneficial to us. And I know there are other folks in the community that are looking to run it on Kubernetes as well. So we're putting a lot of work into that currently to try to improve that experience. And eventually that'll be the default method rather than the Docker Compose method that we have today.
Yeah, and if you want to have a look at that, that's at the Kates-Sandbox repo. Yeah, so going back to...
The fun thing is there's some challenges involved with running Tinkerbell on Kubernetes as well, because I did mention the boot service, which does things like DHCP and TFTP, and it generally expects to be able to talk layer 2 networking directly between the hosts. So for the DHCP process, it's inspecting what is the MAC address of the machine that's talking to me, and trying to ensure that within Kubernetes without just doing something like node ports is problematic, because if you're tying things to a node port, you have other problems in that. How do you handle like reliability of those things? So when you're dealing with the actual ingress or service networking, you lose things like the source IP or the source MAC address of things. And we even explored things like using network plugins like Multis and being able to do things like direct L2 connectivity, and things get really complicated really quick. So I think where we're going to end up settling is probably requiring some type of DHCP relay or DHCP proxy when interacting with it deployed on Kubernetes, so that we don't add in weird, complex CNI requirements that will be difficult to troubleshoot, but eliminate that direct requirement for layer 2 networking between boots and the actual hardware that you're bringing up.
Yeah, that's right. So one of the reasons I didn't want to risk it is I do have the ability to bring up clusters and put in something like Kubernetes advertised BGP and then like set up a DHCP relay, but I don't currently trust the DHCP relay in that switch. So even for my home network, I was using relay, but now it's directly because it just was not working properly. So yeah, we'll get into some of the interesting behavior around DHCP and Pixie, which explains some of the architecture as well. So what we're going to do is we are going to bring up the Docker Compose environment again. The Postgres data is a Docker volume, so just make sure that's cleaned off. Power off the VMs. We basically want to blank the disks. So in this case, we remove the disks from the VMs and create new 100 gig ones that all thin provision, so they don't actually take up that space. Then we start up Docker Compose up, and then we've got one little hack which we need for Cluster API Tinkerbell, which is there's an issue with events in Tinkerbell, which I believe is like currently being overhauled, but we need that for the size of the templates that we're going to be using.
Yeah, we initially created a event-driven workflow for Tinkerbell, and the way that we built it actually had some limitations. So we built it based on top of Postgres triggers, which actually have a size limit. So when we initially tried to do this integration, the first time we created the cloud init data and tried to put it within the metadata, Tinkerbell just returned an error saying the message size was too large. So for the purposes of this demo and older versions of Tinkerbell, you have to disable the events. There will be a new version of Tinkerbell release where we've actually removed the events for now, and we'll reassess how we want to implement that in the future without that size limitation.
Cool. So I guess what I'm going to do is I'm going to bring up this environment-ish thing. Oh, I'll put my... so just going to reset this environment. So come on to the client cluster in a minute as well. All right. Takes a few moments.
And I will say your setup is a whole lot more advanced and powerful than my setup is. Because if I flip my camera over here, this is my home network setup here. The small mini ITX machine running the Tinkerbell components. And then these aren't even NUCs. They're small dual core Celeron machines that I bought, I think, about 4 years ago now. So they are vastly underpowered CPU wise. I think they have 8 gigs of memory so that they can actually run Kubernetes and some type of workloads. But more importantly, for the purposes of running Tinkerbell and deploying Kubernetes to it, these actually have really slow eMMC disks. So things that take about 5 orders of magnitude more to do than if it was like an SSD backed or NVMe backed disk.
Yeah, that's good to know. Yeah, so the vSAN backing environment it's hybrid storage, so it's one flash disk in each server operating as a cache, and then magnetic storage. So I think they're 4 terabyte drives or something, and then it's not quite. It's like RAID 1-ish. It's kind of weird with vSAN. It's not regular RAID. So it's actually doing object replication underneath. So if you looked at Ceph, it's kind of similar in concept, but it's a lot more like it's kind of set it and forget it really. So it's kind of cool. So I've got my got this environment. So I've got some stuff running now in Docker PS. I've got a bunch of things running going at the moment. Next thing you have to do is define some hardware. So we're going to load in, and where do I put that? Here we go, hardware. So got my 5 machines here, and what I've done is these are random UUIDs. Just go to that UUID generator.net and click the button enough times. Doesn't have to be secure or anything, doesn't matter. We are going to be deploying to the SDA disk on all of those. And we're going to give them IP addresses. So given machine 0, 10, machine 1 is 11, etc., etc. Copied the MAC address from the VM information, so on vSphere. So that's how we're going to know what one is what. And we've told it UFI is true. And we've turned on the allow Pixie and allow workflow. So go back to the vSphere environment.
So one thing you mentioned there, I don't want to skim over too quickly, but you did mention defining a disk device in that hardware. And I just wanted to mention that this is a requirement of the Cluster API provider and not of Tinkerbell itself. And basically, as we were going through this, our first iteration, we actually hard-coded this, and the demo that we did was based on virtual hardware. So if you had hardware that didn't have a dev VDA device, it didn't work. So then we started exploring how do we make it work more generally for hardware. And it quickly became messy figuring out how could we detect what disk device to try to do. And we realized that's probably not the best thing to do, because what if we detect the wrong thing? Especially if you look at some like ARM hardware and things, you may have an SD card device in there, and then that is meant to actually hold your bootloader rather than your actual file system. So if we detect that over like an eMMC device or an NVMe device, we could actually overwrite the bootloader instead of storage that's meant for our use. So because of that, we require that the user define within the metadata for the hardware that they're creating what actual disk device that they want to use for the purposes of Cluster API. That way we can, when we generate the templates and the workflows later and the Cloud Init data, it's using the right device later on.
Great. Yeah, I can fully see that. So we are going to load that in. So I've been kind of following the instructions, but I haven't really paid attention to what's actually going on underneath. So we're going to exec into this CLI container, which I guess is a container that has the Tink CLI in it. And we're going to push in these JSON objects which represent each of these machines. I guess they go into the Postgres database.
Yeah, the Docker Compose file does stand up a service running the container that contains the CLI and has the environment variables pre-configured for how to actually talk to Tinkerbell. You could download the binary directly, run it on your host if you pointed it to the right direction. This was just a way to have folks avoid having to actually define those environment variables correctly and or command line arguments every time they want to run a command.
All right. Well, I might just launch that. See which one's the container there. That one. Just Tink. Okay, cool. So I've got this hardware. This. Oh, there you go. Got our 5 machines there. So just gonna. Oh, sorry. Yes.
No, that's fine.
Just gonna see how these are doing. So there's been a change in these machines. They've now booted something. What's going on here?
So at this point, you're going to go ahead and see that It will start the PXE boot workflow, PXE boot process. It should get the hook OS, and it should start executing that and stand by waiting to run workflows.
Okay. And what happens? I can safely just restart this several times, right?
Yeah, absolutely.
All right, so let's do that. Send control delete. There we go. So we got this EFI. So there is already a PXE boot in VM in this VM.
Yep.
So you might think, why do we load another? So we're doing PXE and then we're doing PXE again. Do you want to talk about why we might want to do that?
Yeah, so basically, the network boot environments for various types of hardware vary widely in what type of things they support. Generally, at the very bottom, you can rely that it should at least be able to do a BootP-based protocol, bootstrapping, be able to talk to a TFTP server and retrieve files from the TFTP server and execute those. That's about all that you can rely on being consistent between PXE implementations across default hardware. And while you could take something like iPXE and reflash it on your hardware in some cases and get consistency that way, that's just not realistic to expect everybody to do that just to be able to run something like Tinkerbell. So where we may want to support more things like within Tinkerbell, you can actually in the hardware define an iPXE script that you want to run directly on the host and do things like that. You can specify URL-based booting so that you can boot from an HTTP server and things like that. So that's the purpose of bootstrapping from whatever exists on the hardware into the iPXE environment is that we know that we'll have a consistent environment with support for all of the network boot methods that we want to support within Tinkerbell from that iPXE environment.
Yeah, so, and one thing to note, like TFTP boot, so many years ago, I used to look after the desktop boot and install process for a university, and TFTP boot is extremely slow. Like if you just launching a 200 meg Windows, so Windows has a pre-installation environment, not too dissimilar to what we're looking at here. It's a couple of hundred meg, but it would easily take 10 minutes to download off a pretty decent gig network because TFTP is not really designed around performance anyway. So one of the benefits of using iPXE is that we can switch over immediately to a HTTP protocol and get that performance benefit. And I think you can do strange stuff like iSCSI boot or things like that.
Exactly.
Yeah. So I just got some comments on Valley using AFTP for HPC clusters, which is I've not heard of AFTP. Let's have a quick look what that is. Not that. We might look at that later, I suppose. And I notice I get a shell in this, and it's got, I don't see much going on. Is there, so we now move on to, I guess, maybe a workflow. So what I haven't done here before, so this is new, proper normal TGIK style with doing things for the first time, is how do I run a workflow on a machine without Cluster API being involved? How do I do anything here?
Yeah, so I think the easiest way is if we flip over and go back to the Tinkerbell docs.
Right.
We can go through, there's an example there where you basically just run the hello world Docker container. However, if we do run this, if you haven't preloaded that hello world Docker container into the registry, it will actually fail to run on us. And that's because right now, Tinkerbell defaults to, when it's running the workflows, defaults to prepending the registry URL that you configure for it. So it assumes that you're going to have that standalone kind of on-premises registry. However, we're looking at enabling direct upstream registry support with it to kind of limit some of the barriers to entry for the bootstrapping process for folks that don't necessarily want to run their own registry. But here, if we look at the docs, and let me see on my end as well, when you define a template, and it looks like it defines a template down there a little bit lower, you can see it's just a basic YAML document that you create, and you basically just define the steps that you want, and those steps are specific actions, and those actions link to some type of container image. And we actually publish some pre-configured actions to our Action Hub, which actually runs on the CNCF through the CNCF artifact repository, so that you can go there, find these predetermined actions, and you don't necessarily have to write your own container image to do some of the more common things that you'd want to do in Tinkerbell.
Okay. So I'll just give this a go. So I need to pull down this image into Heagle, and then I need to tag that with this address, and then I need to push it.
Yep.
Okay, so we have it in the repository, and we'll just where's good to run it from? We'll just put it here. That's all I need. That's a workflow. So
Well, that's the template.
oh, okay. So this is template, and I guess it looks vaguely similar to it, something like Ansible or something, where you've got a bunch of actions that's going to happen.
Yeah, and basically these are being these containers are being run in this case with Hook. It's running within the Linux Kit environment. There's a couple of other additional services running in there, and you can mount in host directories. They're running with privileged mode, so you can access anything on the local system that you would otherwise be able to if you were running natively, with some exceptions, because things like reboot and kexec actions require a little bit more trickiness. But either way, you can mostly assume that they're running local on the system.
Okay, cool. So now we're gonna try and load this in. So, yeah. So the container is not gonna have access to my local disk, is it? Exactly. Do I do that? Oh, that's a step too far. So I need to create a template. I need to push the template somewhere.
Yeah. So what you can do here is you can basically run on this on the local host. You can use the Docker exec and then redirect the contents of that file into standard in for the Docker exec when you run the template create command with Tink.
Oh, okay. So I can do just a cat on that.
Yeah.
And then pipe it in. And then I have not looked at the commands.
It should be similar to the command that you ran for the hardware, just for the template create.
Okay. Okay, cool. Let's put that. Confuse ourselves. Think template create, and is it like that?
I think you have to give it a -- file and then a dash after that.
Oh, it's one file.
Let me look. Let's see how I did it on the hardware.
It's that.
Okay, so I think you're going to have an issue trying to use the pipe. I think you need to redirect the standard in after the Docker command.
Oh, how do I do that? That's the
So just should be similar to the command you ran up there for the hardware create.
oh right, yes. Let's have a look at that one. Yeah, so that people watching, you know, my I thought I did that. Oh, without the T. Okay, fine. I'm not the I'm not a bash expert. Don't.
Well, it got tricky too because I believe if you use the depending on whether you're using the pipe or redirecting the standard in, it operates slightly differently as well.
Oh, actually, it probably would have worked if I didn't put the T, because obviously a pipe is not a TTY. That's right.
Yeah.
Okay. Right. Okay. So now I've got a template in there. Right. So it's got a template ID. Did we create a template ID, or was that something the system did?
That's something the system did. It'll
Okay,
automatically create that. And now that we have a template and we have hardware, now at this point we can create the workflow to do that. And there's a kind of template syntax that you have to use. So if you take a look at the example there, and what this is doing is inside of the template, we defined a placeholder for the hardware itself. So with the workflow command, what we're doing is we're telling it to take the template that we created and apply it to the hardware that we're specifying via this other argument.
Okay. So we need to take this template ID.
Yep.
Write that here. And then that device one, I can put the IP address. I guess that would be easiest.
Yep.
We just alias that. There we go. Right. So now we've got a workflow, and if I go to the machine, something happens?
So yes, however, you're not really going to be able to see much because the hello world example here is running in a container and it's basically just echoing hello world out to standard out. So we could go into this instance and we could go into the container and we can introspect the output and do all of that stuff, but that's kind of painful. So in this case, what is probably easiest to do is just look at the what is the state of that workflow. So if we go back to the tink command, if we just hit enter there, you'll see that there's other subcommands for workflow. And well, if you do a get, it's just going to show the workflow itself. There are other subcommands that let you see things like the events associated with that workflow or the state of it. So if we look at the state, we should see that the state is completed for it.
Made a note of this one. Okay. Okay, right. So we got, and we have this state success. So it succeeded. So what happens if it fails somehow? What?
So this is the overall state of the workflow. You would see that there would be a failure, and then you can look at the actual individual events, and you would see what events for that workflow actually completed and which haven't.
Okay, cool. And does stuff retry if it fails, or is it just it's a one-time execution?
Yeah, so it depends on how the failure occurs. And one of the things that we'll see when we investigate things a little bit further is at this point, some of the actions like kexec and reboot don't actually finish. So the workflow stays in a partially completed state. And during a reboot, it actually goes through and reruns that last action. So any hardware that's configured to run the workflow for Cluster API, if that hardware is rebooted, it'll actually start running the workflow again and kexec into the kernel that was installed on the machine, and it'll just continually do that every time it's rebooted. But if it had a hard failure, it won't necessarily retry that. You would be expected to create a new template and/or workflow to re-execute it, just because we can't be sure it would be safe to retry or not.
Okay, cool. Yeah, that makes sense. And how are things communicating? How does the machine know that it's got something to run, a Docker container to download and execute?
Yeah, so basically what's happening is when the machine is given that initial hook or OC image and boots into that, there's a service running on there that's doing nothing but polling the Tinkerbell service and saying, is there a job for me to run? It's running this Tink worker process, just sitting there waiting to actually do something. So that's the only purpose really of either hook or OC in this case, is just, is there any work for me to do or not? Do I continue sitting here, or if things are complete, or do I need to reboot, things like that? All of that's happening through the definitions of the workflow rather than the hook or OC image.
All right, so my machine is connecting to this port, I suppose, and polling it, and figuring stuff out, what it needs to do, and cool. And how are things like secured between the different components?
So that depends. Right now, we've been mostly focused on feature completeness. Most people are running this in a data center, not needing to worry necessarily about traffic being sniffed on the local network, that sort of thing. But we do plan on doing further work on security, and we'll probably try to push it out more towards the edge with the Kubernetes-based deployment. So TLS would be terminated at the ingress point, and you'd have more clear traffic going on beyond there. But we do want to make sure that we enable that security over time. Just it hasn't been a priority as of yet.
Yeah, that's fair enough. So, and at any moment, has this Heagle been involved, the metadata endpoint, or is that going to be used when we start bootstrapping with Cluster API?
So right now, it really hasn't been involved. There is some integration with some of the other components as far as Heagle is concerned, but nothing that would really impact what's going on here. We're going to see it come in more to play when we're generating that Cloud Init bootstrapping data with Cluster API.
Cool. And I guess that's what we'll give a go right now. So what I'm going to do, I'm going to use Kind. So if you're not familiar with Kind is a way to run Kubernetes clusters in your local environment using Docker. So it's Kubernetes in Docker, and you can get that with Brew. Brew install Kind will get you that, and you can go to the website. Kind Kubernetes. And yeah, so you can got the quick start here. So we're just going to create cluster. So it's just going to be a single node control plane, and that's just with a Kind create cluster. So it's going to live alongside all the other Docker containers. So this node image is I think something a bit like a Debian or Ubuntu. Looks like a bit like a host image. So it's got a systemd in it. Boots kubelet, runs containerd, and is going to run kubeadm, which is a Kubernetes bootstrapping tool. So these are all kind of components that we're using in Cluster API as well. Yeah, it shouldn't take long. It's a bit slower than my desktop, but it gets there. I did have to bump up the RAM and the CPUs on this quite a bit. All right, should be ready in a minute. And what we're also going to use is we're going to use something called tilt. which if you haven't seen the video from Ellen Corbs, did release a quite amusing video on what Tilt is all about. It's in the show notes, so go take a look at that if you want. Not now. Do not go to the link now. Go later after this live stream. So Tilt is a way. It's like a local development environment. It operates against the Kubernetes cluster that you got locally. In this case, the Kind cluster. It allows you to do hot reload of code. So you can make changes to your code and have those containers rebuilt within seconds and running. So we've supported Tilt in Cluster API as a development tool for a long time. We'll not go into the details of that Tilt setup. So there is a Tilt file that ships with Cluster API. It's written in Starlark language, Starlark, the one that Basil uses. And we have some settings that you need to put into Cluster API if you're using it with Tilt. So you have to configure this. I don't think you really have to configure this default registry, but that just happens to be a Google container registry. We're going to load in the Tinkerbell provider, which is in an adjacent directory, and finally we're going to enable Tinkerbell and the different components of Cluster API. So if you want to, not like I said, we're not going to go into massive details around Cluster API architecture and stuff. Oh, that's the wrong book. But you can go to the cluster API.sigs.kates.io, and we've got all the documentation there. So there's a bunch of components. Nevertheless, there's a bunch of components. There's a core cluster API component. There's something called KubeADM Bootstrap, and that ties in with the Heagle stuff we're just discussing a moment ago. So it generates cloud init boot data, and KubeADM control plane, which is a stateful control plane management controller. We're going to give it some stuff. You can ignore this X cluster resource set. We're not using it really. We're giving it the we're basically pointing it at the Tinkerbell server, and then finally got the Tinkerbell IP. And given that I've got that Tilt, that Kind clusters come up successfully, I'm going to go into the Cluster API directory, and I'm just going to check something here. Yeah, so it's now doing some stuff, and hopefully I have tunneled this correctly. So this is running on that sandbox VM in this other SSH port forwarding. Yeah, so I should be able to. Oh. Apologies, I just locked my desktop. That's all sharing. That's all good. Right. Right. So let's not do. Oh, okay. Yeah. So it's loaded in a bunch of custom resource definitions that Cluster API uses. We'll go through some of those, what those are in a minute. And I believe it's going to start building a bunch of stuff. I have previously ran this before, so it does take advantage of cache builds, or at least the way that we set up in Cluster API. So a lot of these haven't really changed the code, so it's going to take use of it's going to make use of the Go build cache. The Docker layers won't have been changed, so it should be mostly a matter of loading in the Cluster API components. And they should be up in a minute or two. So whilst that's happening, we'll go through the cluster that we are going to deploy into this Kubernetes cluster. So let's shrink that. There you go. There you go. Right. So first, we're going to give it a pool of resources. So we need to tell the Cluster API provider for Tinkerbell what hardware we're going to use? It's just going to act as a pool of hardware. Is that right, Jason?
Yeah, so basically what we did is we could have just created a provider implementation that just talked directly to Tinkerbell itself. But one of the things we wanted to be cautious of is that we didn't just assume all hardware available in Tinkerbell is available for us to use within Cluster API. So we have what we've called a shim layers in as well, where we define CRDs and have controllers that match up against the actual Tinkerbell resources themselves. In this case, the hardware that we're defining matches hardware resources, and it'll expect that hardware already exists in Tinkerbell. And once you create that, you'll actually be able to see the status and all the things that exist and are defined in Tinkerbell directly here. But that shim layer also allows you, while it doesn't allow you to actually create hardware in Tinkerbell right now, it'll actually allow you to create those templates and the workflows that we were looking at doing against Tinkerbell itself. You can create those as Kubernetes resources rather than having to talk directly to Tinkerbell.
Oh, cool. So those workflow and template YAMLs, I could have applied them directly through Kubernetes.
For the template and the workflows, yes, not for the
cool.
hardware today.
Okay, great. So next up, we've got a cluster definition, which is in a weird order, but never mind. So we have a Kubernetes cluster a cluster API cluster resource, which is called demo. It's going to be in its own namespace. Probably didn't need to do that, but anyway. Pod CIDR, so that's going to be, just what pod network is going to be used, what service and service CIDR bog standard stuff there. We've got a definition for the control plane. So this uses kubeadm underneath. So what way Cluster API is going to work? It's going to create some machines. And it's going to get kubeadm, which is a kubeadm is a CLI that can instantiate a Kubernetes cluster if the machine has kubelet and containerd installed. It will download the images from the GCR where all the Kubernetes artifacts live. It will configure static pods, so you can put pod definitions in /etc/kubernetes/manifest, and kubelet will just run them. So it sets up etcd API server and just runs them. So one thing that I did see that was interesting is, so if you're working with a public cloud, a provider ID is going to be something like your instance ID. What you have in a Kubernetes cluster is a cloud provider integration. So it's a mechanism that can connect to that API, whether that's AWS, GCP, vSphere, and is able to get some information about that host and find out what the unique identifier is. So I guess we're dealing with like generic hardware, so that doesn't exist. So instead we've just got this provider ID. What's going on here?
So yeah, you mentioned the cloud provider interface. Eventually, we may create a cloud provider for Tinkerbell, but we didn't want to make that a prerequisite for being able to get something going. So basically, all we're doing today is we're passing it in as arguments within the template, and the controller itself will actually get the provider, it'll get the hardware ID and it'll generate that provider ID itself. So Cluster API takes care of that. And because we're setting it through the config, that ends up getting associated with the node at creation time rather than needing the cloud provider controller to come through and set it after the fact.
Great, thanks. And I'm not sure if I needed to set this. I think I've kind of screwed up my deployment initially, but so I've got a machine template for Tinkerbell, and I've set the image lookup base URL to the local repository. I think I originally had I misconfigured it as 192.168.1.1 when it wasn't 192.168.1.1 at all. The whole thing exploded. So I've got that set up.
If that's not specified, it'll default to using that Tinkerbell IP to associate with the default sandbox configuration.
Right. Yeah. Yeah, that's what I noticed later. And so we've got so if you're looking at this for one of the other providers for the AWS, you would declare what instance type you're using, like what disks you're going to attach and those kind of things. So given that these are bare metal, don't really need a lot of information around
And
that.
we'll eventually want to add in support for that as well, so that you can define via the metadata more details about the hardware, and you can select hardware based on that. But it seemed a little overkill for the initial implementation to try to predefine what that should look like. So we figured start with just using the hardware that you predefine through the shim interface, and then we can figure out how we want to add selection capabilities later. I did want to skip back to something that you did kind of fly over there, but in general, if you're using the sandbox deployment, or I think even with the network configuration that you have on your local machine, if we had left the pod CIDR block to the default configuration, you would potentially have a conflict between the local network configuration and the pod network when we deploy CNI later.
Yeah, that's right, because I think it uses 192.168.1/whatever. So yes, if you've ever had the misfortune of deploying Kubernetes cluster where the pod IPs clash with the node IPs, very strange things start to happen with your network. Do always be aware of that. Yeah, we've been thinking about, I think, for a long time, trying to put some logic into Cluster API to sort of detect where you might be about to clash. I think that there is an open issue around that. PRs are welcome.
Well, and that's always challenging too, because right now we don't assume that the core Cluster API components really know anything about the infrastructure providers. And when we're talking about things like this, you actually need to get that information from the infrastructure provider, generally what we would call the cluster infrastructure provider, to say what is the network that we would expect these hosts to be deployed on. So it's almost a challenge, like, how do we make that information available without doing things like creating a whole new CRD resource and a whole new set of controllers to do nothing but kind of ferry that information back and forth. So it's a quite complicated problem when we look at it.
Yeah, that's right. And then we've got a machine deployment. So if you're not familiar with Cluster API, so machine deployment is very much like a deployment in Kubernetes. So except we're using machines. So we use a similar sort of abstraction behavior in Cluster API. So we have a machine, groups of machines and machine sets, and then we're able to do upgrades or rollouts between of machines using machine deployments, which will then scale down a machine set, create a new one, and scale that one up, etc. So very similar. If you're familiar with Kubernetes resources, this shouldn't be. The idea is it shouldn't be completely abstract for you. And then we've finally got a kubeadm config template. So these are going to be used by the worker nodes. So separate. So it looks a bit similar to the control plane because we're using kubeadm underneath. So it's pretty much very similar to that, except it doesn't need the information about the stuff that's only going to be on the API server. So we are going to load this in. I need to. Okay, so created a sandbox. And I'm going to first add the hardware in. Oh, sorry. Oh, it all affects on me doing that, right? I think you're mute. You're mute, Jason.
Sorry. Yeah, so I was going to say this actually didn't have an effect because the hardware template and the workflow resources right now are cluster scope, not namespace scoped. And that was just because we haven't defined yet a multi-tenant story around how do we want to talk to multiple Tinkerbell services. So that's something that we're looking to solve in the future, just not now.
Oh, okay. I wondered why it was working before. That explains things. All right. So you can see it's pulled information from the Tink server. So in the status, and one of the handy things about using Tilt for this is we can browse the logs as well for these controllers. So we can see some information coming in here. It's all nicely JSON formatted if you want to put in that in your log ingest server. Yes, that's pretty good. And then now we're actually gonna deploy that server. So, all right, we've created some resources, and see we've got one control plane machine. So what's happening is the Kubernetes control plane controller has templated out a machine that's going to act as the control plane. Tinkerbell has then matched this with one of the hardware pool. One thing that is there an easy way right now to find out what machine that is?
So not right now. We could have chosen to do something other than the UUID for the provider ID. However, I wanted to avoid any potential issues that if machines are mutated in some way and IPs are changed and things like that, that you don't generally match up with something. And since that UUID is the distinct identifier for Tinkerbell, the UUID made a lot of sense there. On my local environment, I actually cheated a little bit and I modified the UUIDs so that I can easily know which machine is associated with which UUID. That's really hard to say, by the way.
Pro tip. Yeah, so I guess we've probably seen so far, I noticed that we have some stuff that's loaded. Something's happened on this machine. And one of the things that was interesting, so what I can do here is we should see a whole bunch of traffic going from the HTTP. Yeah. So it's downloading something from the HTTP server, and that would be that if we go back to VS Code, that if we go back into the webroot, is it's downloading this image, this Ubuntu. I guess
so if we actually look at,
sorry.
I was going to say, we can actually do a kubectl describe on the template, and you can actually see the list of actions that are going to be performed on that host through there. And this was all generated by the Cluster API provider Tinkerbell controller.
Oh, okay. So, right. So it's going to stream this image. So I guess it downloads it into memory and then unpacks it.
So it actually does it mostly through a pipe. So it's going to compress it through a pipe and write it at the same time. So it uses it'll use memory basically for a buffer, but you don't necessarily need all the memory available for the image there.
Cool. And then the next thing it does is it's gonna write a cloud init config, and
yes,
it's doing something a bit interesting here, isn't it? So it's changing that endpoint.
Well, and right now, because we are using a Heagle for the metadata service, and it is somewhat EC2 compatible, what this is doing is basically writing the configurations to tell Cloud Init to use the EC2 metadata. Make sure to not treat it as a strict EC2 metadata instance, otherwise it'll fail. And it defines a default system user that you can then assign later an SSH key or a password to through the cluster template if you wanted to be able to access it. And Because Cloud Init is a bit wonky at times, you'll see that right below writing that file, we write another file, which forces the metadata configuration to work too, because when it's bootstrapping, you have fun things like determining which metadata service to use is done multiple times. So we have to define it in 2 places to force the EC2 metadata service to be used. The other thing is all of the things that are happening in Cloud Init are happening before the network service comes online, because we're not fully compliant with an EC2 metadata service. And if you do a detection from the local host and you do a DMI decode, it doesn't show as Amazon hardware to trigger the EC2 metadata service. If we're going to interact with metadata, it has to happen before the networking stack is brought up. And that's the purpose of why we're using that 169.254 address. That's actually a link local address that's available before you actually configure networking on a machine.
Ah, interesting. I didn't realize that. Oh, yeah. Cool. I don't know how that's working on the switch level. I guess it works. I did notice this warning thing. I guess it's just an extraneous event that's been from controller runtime, I guess. That's yeah. And let's see how this might be ready, actually.
And another thing too is at that last little bit there, where it's saying where to kexec into. This was fun too, because depending on what type of block device you're using, determining what the first partition should be on that device differs based on the type of block device. So in the case of things like SDA, HDA, and VDA, you just append a numeric digit to the end of it. But if you're dealing with an NVMe device or an eMMC device, you actually have to put a different suffix on the end of it so that it can find the right partition.
Ah, right, yeah, that makes sense. So I believe this machine, it's already rebooted into Ubuntu. So the kexec allows it to not have to actually do a full reboot, right?
That's what I was going to say, is it's not actually rebooting. After it writes it, once it gets to that kexec action, it's going to actually load that kernel into memory and replace itself with the kernel that we just wrote to disk.
Right. So you can see here, got the output. We need to check actually with the other Cluster API providers. We probably should not be displaying the join token on the console, but I think that's the issue with all of our providers. We probably need to check that. But you can see the kubeadm's finished, and if we go to here, and you can do kget kcp, and we can see we have it initialized. Control plane, it's not ready, and there is a reason for that. Which I can forgot the command now. Wait a second. So just going to switch to this new control plane. Right, so we have a not ready node. So Cluster API is more or less happy to continue with that. And the reason it is because we haven't got a CNI installed. So I'm just going to quickly install a CNI. VMware, so I'm going to install Antrea.
And I think the biggest thing here is to keep in mind when you're installing the CNI, some of the CNI providers require you to pass in configuration if the pod CIDR doesn't match the default one used by kubeadm and Kubernetes. So in this case, Antrea doesn't require that, so we can just apply it without worrying about it. If we used, I think, older versions of Calico, you would actually have to modify the CNI deployment before you deployed to it, because we are using that non-standard pod CIDR.
Yeah, I think they fixed that in the Calico operator, but not sure. So yeah, we know this one works. Well, or at least it got me to a ready state eventually. Does take a little while to download though. Where you could have been, yeah. So I only have ADSL here, so it's not kicking. It's not kicking into that. So that's what that is. If I do unset kubectl, so go back to. So we still have the one. Oh yeah, we haven't actually defined any machines in the. Forgot about that. I was like sitting there watching. It's like, oh, why haven't I got any other machines? It's like, oh yeah, it's not. Replicas are 0, so that would be why.
Once you scale up the machine deployment here, you'll be able to bring up worker machines. We haven't yet added support for HA control planes yet. That's one of the things we're going to be looking to do here in the upcoming months. We're going to leverage the new CNCF Sandbox project KubeVip to be able to deploy an HA control plane. However, there's some challenges there because what IP do we use for that? So we need to solve how do we do that IP address management because we've deferred it with the actual hardware instances by requiring that being predefined in Tinkerbell. But for the purposes of assigning an IP to KubeVip, we'll need to actually have an actual usable IP address that's not going to conflict with anything else on the network.
Yeah, yeah, that makes sense. Yeah, so I mean, we have those requirements of bare metal are not dissimilar to everything in on any sort of on-premise environment if you're using vSphere as well. So that's an area where we're going to work together. And just to make sure, you might be thinking, oh, VMware and bare metal. It's like, well, for the way we see it is, if you're going to deploy a Kubernetes cluster, you want to have it on some form of programmable infrastructure, all right? And vSphere provides that for you. AWS provides that for you. We have well-defined APIs that spent many years in the making, and that makes it super easy to get a fully featured environment. You can deploy a Kubernetes cluster in vSphere, and you're going to get stuff like vSAN. You're going to get provision volumes and all those sort of cloud type benefits, right? So if we're going to do that on bare metal, we're going to have to make that bare metal programmable in some way, right? And this is where projects like Tinkerbell are showing that promise in terms of providing a programmable infrastructure for bare metal. So it's a really interesting space for us, and like a lot of the similar concerns. So this is an exciting area.
And I think one of the most exciting things for me is I think you see a lot of the existing work that's been done on doing Kubernetes within the data center. And a lot of that work tends to be, it tends to adopt a lot of the practices of how you manage hardware prior to cloud native methodologies. So you tend to want to support things like doing things in place because doing things like rebooting a server in a data center can take anywhere from like 10 to 20 minutes, depending on what needs to happen to initialize the hardware at boot time, things like that. So, what we really wanted to try to do when we developed the Cluster API for Tinkerbell is could we take a real modern cloud native approach and do it with hardware? And so far, it looks really promising. Things like being able to do the kexec into the kernel means that we don't have to do that reboot and wait for that infrastructure to come back up. Things like being able to leverage a Heagle metadata service means that we can leverage things like Cloud Init and predefined OS images like golden OS images that are streamed on demand and treated like ephemeral instances. And sure, we do have some problems to solve, like how do you run stateful workloads in this environment? But I think that we're starting to show the promise of what it really means to do cloud native management of bare metal infrastructure.
Oh, thanks. So I actually just got the kubeconfig back, and it's now not working.
Oh no!
Oh dear. Maybe I did need to configure that entree, and I've now balked its networking. Yeah. I know, but I still think, don't know what's happened. So what have we got here?
And this is the fun of live demos.
Yeah, that's right. Also, I bet my host is one of them screaming at me right now. There we go. Right.
Did you want your screen up, Nadir?
Oh, yeah, that's right. Yeah, so one of my hosts has got a big red alarm next to it, complaining about memory usage and CPU. So that's fun. So that's all very normal. There's not a lot of memory in these consumer grade hardware. It's just being slow. It's fine. Okay, probably saturated the network and overloaded the CPU. So it's fine. So got some of the other machines coming up. They will go to ready as they download Antrea and get running. But we're just talking about them actually deploying on hardware. So maybe I'll hand it to you, Jason. You've actually got your real bare metal rather than my fake bare metal.
Yeah, I mean, my bare metal is still kind of fake bare metal in that it doesn't have server grade baseband management. But I think that it makes it kind of fun too, because let me switch my camera over here. So have a little there in the corner, I have my actual infrastructure. I'm going to speed through this a little bit because it's going to be a lot of what Nadir just showed. But let me go ahead and create the actual hardware resources. I've already stood up Tinkerbell, predefined the hardware in Tinkerbell. I already have my Cluster API stuff already up and running. So now I've created that hardware, and let me copy and paste the command for creating the cluster because I want to make sure to override that pod CIDR as well. So in my case, I'm just going to use the cluster cuddle command. And because the image that I built it a little while back, I'll actually be deploying Kubernetes 1.18.15 to match the image that I pre-built. I'm going to override the pod CIDR to 172.25.0.0 because in my case, the network that I'm deploying on is 192.168.1.0/24. So that would conflict with the default pod CIDR. So now if I Cluster API here, I'll be able to see which machine was assigned to it. In this case, I did say that I cheated with my UUIDs a little bit, so I know that this is the hardware that I marked here at A. So let me go ahead and power that on. And when I mentioned that this hardware was a little bit older, it's not going to boot up as fast as Nadir's VMs did. So where his probably booted up in roughly a minute or two, this machine will actually take about 5 minutes to fully bootstrap. And again, because I don't have remote management, I don't have a way to show the console on that machine kind of nicely. But similar to everything else, it'll be going on in the background. I can go ahead and get the kube config for this cluster, and it'll mostly just sit here if I tried to do a get nodes on it until that finishes bootstrapping and everything. I don't necessarily want to keep everybody waiting on that. So while that's processing, is there anything else that we wanted to talk about? And we can go back when this has had a chance to actually stream that image to disk and actually boot up.
Yeah, let's go through some of the comments because I have not been paying attention. So this is not as polished as maybe some of the previous hosts, like Joe, i.e. not Joe. We've got one question. Is the new Bootstrap OS also written in C or Go? I guess that's referring to Hook and OC.
Yeah, so OC is very much more of a traditional type of OS image. So I believe it's based off of Alpine. So it basically looks and feels a lot like an Alpine OS. There's some shell scripts involved with OC to bootstrap the Tink worker. The Tink worker itself is written in Go. But when we look at what's going on with Hook instead, like I said, it's a much more streamlined OS. So it's also sort of Alpine based in that it's based off of Linux Kit. But Linux Kit actually is a way to declaratively build more or less a Linux distribution. So it has a look and feel similar to Alpine, but when you get into it, things like troubleshooting it are slightly different. Everything's run within, it runs Containerd by default. All of the services that run within the OS are run within Containerd, and that sort of thing. So it's not as easy as saying whether it's written in C or anything, because just like the kernel, like normal kernel and things like that, for the Linux kernel, those are written in C. But the interesting thing for Hook is the services that we're running. We run a Docker service in there so that you have the normal Docker interface instead of having to rewrite the actions and TinkWorker to interact with Containerd directly. So that's just standard Docker service running in there. So Docker's generally written in Go. But then there's some of the helper things like the tool to write TinkWorker. There's a restart helper to be able to help issue restarts and things like that, because you can't do that directly from a container without some additional help on the host side. But I hope that answers the question, because it's a really complicated answer or question to answer. But where possible, we use Go when we're writing something ourselves, just because that's what we're mostly familiar with.
Yeah, that makes sense. So I guess Linux Kit's userland, where it differs from a standard Linux distribution, is Go based. But you're not. It's going to be a long time before we move away from C. I mean, we are talking about Rust appearing in the Linux kernel. We'll see where that goes. Had some questions about the home labs. I am probably not the best person to talk about home labs if you want demos. William Lamb, and I will put a link in the show notes. William Lamb has a website which has everything you ever want to know about vSphere home labs and how to build them cost effectively, how to get discounts and that kind of stuff. And I'm sure there's a lot of YouTube. I will try and dig out some YouTubes where he's gone through that home labs and put them up. Got a question from Jay, interested in the Vagrant recipe. I guess this is particular relevance because a lot of the Kubernetes on Windows work is being done in Vagrant. Do you want to show that?
Yeah. So the Vagrant setup, it's kind of weird. And let me see here. Let me open up a new window here, and I can switch over to the sandbox.
Well, I can show it from mine actually. If that's easier.
Oh no, this is fine. I got it right here. So in the sandbox, we do have the Vagrant file. A lot of the things that are happening to actually configure Tinkerbell aren't actually happening in the Vagrant file itself. But we did have to do some funky things in the Vagrant file to make things work. One of them is we don't enable, we want to make sure that we're not doing parallel instantiation, just because we don't want the workers coming up with the initial provisioner machine. Otherwise, you end up with some weirdness there around the type of networks that you're defining, because we define the network for communication between the workers and the provisioner when we define the provisioner, and then we just use it in the worker. So if we try to bring those up in parallel, you'd get weird failures. Being able to do things like configure the number of workers, whether you want to enable the GUI if you're using VirtualBox. We do have some of the fun things, like you can disable configuring the NAT. So like on my setup, I don't configure the NAT, so I opt out of that and don't have to worry about things forwarding from the worker machine through the provisioner. Because if you start looking at the way that like VirtualBox does networking, if you stand up a separate network, you can't define a gateway on that network to be able to directly NAT out of the bridge device, but you can do that in libvirt. So this combination of this configure NAT and this libvirt forward mode give you a way to basically opt out of the NAT and be able to do direct network connection from the individual worker VMs out to the internet directly, but we can't do that with VirtualBox. And if we supported other providers, how do you configure networking across those gets fractal and messy pretty quick. The other thing is everything stays pretty similar. In here, I upgraded the latest Fedora version, and I found out that now it defaults to trying to use the user session with the Vagrant provider. And that causes all sorts of weird things when you're trying to do funky things with networking. So I need to see if we can add something upstream to better support that use case where it tries to detect the right thing. And then here, all we're doing is syncing the folder, and this is making sure that that state information that's available on the local machine is available within that Vagrant box. For libvirt, it does that automatically over NFS by default. I don't remember what VirtualBox does, but that's so that things can bootstrap faster a second time if we have to. And things like the OC image were like 2 gigs. So it's like, if you had to like bring the environment down and bring it back up, you had to wait for 2 gigs to download over whatever network connection you had. And that was messy. Here's where we're doing some of the network stuff. We're basically telling it, to use a private network for the purposes of being able to talk to the worker machines. There's always a default network adapter that's configured for the purposes of being able to talk to the host and back, and trying to make sure that everything talks right and the right traffic's going over everything. So we had to do a lot of playing around and trial error to make sure that everything works there. Other things we're doing is we're forwarding the ports so that if you wanted to talk to Tinkerbell directly from the local host, you can do that. But other than that, there's not much to do. We do have a minimal set of memory that we want to make sure that the provisioner has, that sort of thing. All that's pretty standard, I think, though. The workers get pretty interesting because we try to sit there and just have the one layer 2 network only, and telling Vagrant how do you disable the host only connection gets a little bit weird. So we had to play around there a little bit. But yeah.
Cool, thanks. Hope that answers your questions, Jay. So I'll going back earlier with a little comment. So I was looking up the wrong thing. Got it's a TFTP to speed up TFTP downloads. So from looks of things, it uses multicast, which is I think something that the Windows pre-installation environment supported as well back in the day. Little comment about in HPC environments using BitTorrent to speed up boots for whole HPC clusters. Fairly interesting. So that's pretty cool. That's the end of the questions. How's your host doing, Jason?
Well, we do have the hardware available now, and we do have a not ready node. In my case, I'll be deploying Cilium to there just because that's another network provider that doesn't require you to configure the pod CIDR by default. And similar, I don't necessarily see a point in going too far through this, but once that CNI is available, this will show is ready. I could also scale up those machine deployments in a similar way, and that's running on this little funky hardware setup that doesn't actually support a lot. One of the few things that actually does support is being able to do default network booting. But other than that, it's got no baseband management. They're really old dual-core Celeron processors, I think somewhere between 4 and 8 gigs of memory, and a really, really slow eMMC disk that doesn't even perform anywhere near what an SSD or even most SD cards would do for throughput. So it takes about generally about 5 minutes to bootstrap these instances compared to something that would be faster, which would be closer to like a minute.
Cool. And I noticed like when I built Hook, there was an ARM image. So can this work with the say Raspberry Pi bits and pieces? I haven't really looked at how Pixie works in Raspberry Pi.
So from the perspective of Tinkerbell itself, yes, it does support being able to bootstrap ARM hardware. I've had some fun because all of the ARM hardware that I own is really funky around network booting. Like one of the devices I have is a macchiato bin, and depending on how you boot the instance, you can get UEFI hardware for it. They have a build of EDK2 that you can put on there. But what you see with it is when it gets to Linux, the ACPI information doesn't get transferred over to the Linux kernel after the boot process comes up. So it comes up with a completely different MAC address, so it doesn't actually finish bootstrapping properly. The second time it DHCPs, it gets it doesn't get an IP address because the MAC address doesn't match what you configured originally, and it uses like a weird default MAC address scheme that you can't even tell hardware to be because it's not even a legal MAC address. And I don't have any newer Raspberry Pi 4s that support proper network booting, and the Raspberry Pi 3s that I have don't quite have support for it. So, Tinkerbell itself does. The Cluster API bits, the biggest thing that's holding us up right now for that is support an image builder for ARM-based devices. There's a lot of stuff that's hard-coded to x86 specific packages and binaries right now, but we do plan on helping contribute support for ARM within image builder, and then adding in probably a field to be able to select what type of architecture that you want for the OS, so that we can do the right thing, like build the right image name to use to stream the image, and also for even determining what you want by default, which will probably default to x86 for now because that's still the most common. But ARM is definitely something that we're going to be looking at doing later this year.
Sounds cool. Yeah, well, I mean, we definitely need to get the ARM support sorted out for AWS as well. So, got one last question we'll take. I have a couple of old laptops. Can I run Tinkerbell on my Ubuntu machine and boot those machines using Tinkerbell?
So very likely you should be able to do that. The biggest thing would be is, does the hardware actually support network booting? Because there is some hardware that doesn't. I think most modern hardware now does. But if you look back, like I know a decade ago, if you didn't have the right network card in your machine and it didn't have a boot ROM, physical boot ROM chip on it, it couldn't actually network boot. But I think with UEFI, most hardware is capable of it now.
Yeah, I think one of the interesting things, you probably need to have an Ethernet port with that laptop, and with a USB Ethernet, that's not going to have the boot ROM. So yeah, if it's like a Lenovo or Dell, and they've got physical Ethernet ports built in, or you're able to plug in a PCIe Express one with a boot ROM, then I think you should be good to go. But yeah, have a look.
Yeah, and for the Pi 4, I haven't actually played around with them. I don't know if you can use the default OS, the default U-boot that's available on the Pi 4 to be able to do a direct compatible network boot. I know in previous Pi instances, you had to configure network boot differently in order for the Pi to be able to network boot. But there is a UEFI firmware that you can deploy on the Pi 4 that should work completely out of the box with Tinkerbell.
Yep. And to run the FTP server, does it have to be on the host, or can it run on kind? You need to expose that TFTP server onto the network. Don't know if that's even possible in kind, especially if it's running on Mac OS or on your Ubuntu machine. You say, if you're able to port forward it somehow, and maybe there's instructions in kind to do that, then maybe it might work.
Yeah. So I went down a big rabbit hole with this, and I spent a couple of months trying to see if I could stand up everything that you would need to be able to deploy Cluster API and Tinkerbell into just a kind cluster. And it gets really messy with the way that networking works, especially if you're looking at non-Linux OSs. because on a Linux OS, you can tell Kind to use a specific bridge on the Linux host, and then you can access direct traffic to the Kind instance there. So you could do things like expose boots on a node port on that Kind cluster to a specific network bridge, and then as long as you have a VM or whatever on the machine connected to that bridge, everything would work great. However, the way that things like the networking with Macs and Windows work, it's not that direct. You can't just connect local VMs to that. And that got me down to what if I just ran the VMs inside of Kind as well using KubeVirt. And that got ugly because then you start having to deal with things like Multis as a CNI solution and being able to enable direct L2 networking between the machines. And even when I did that using things like Multis with the CNI bridge interface, you still get weird things like the IP address getting rerouted. And it turned out that I thought there was going to be a solution with one of the different types of networkings settings that would allow you to sit there and basically short circuit having to run through IP tables for the bridge network. But that only works if you're using it on a physical machine because it creates the interface on the actual physical host, even if you create it in a container. So it's really messy once you're talking about trying to do pure L2 networking directly in a Kind server.
Yeah, that makes sense. Yeah, it will get tricky. So I think just asking if you have pointers, links, and running all Kind from a Linux machine. I think you should go to the Kate Sandbox repo. Is probably the best place to go. And issues.
So probably not today, only because that Kate Sandbox is also running in Vagrant right now. It's just setting up the Kubernetes deployment on the provisioner machine. And that was basically to avoid the same type of networking mess that we're talking about here. I don't know if I have any documentation to get it all working from a Linux machine directly, but there's a flag that you can pass to Kind, or maybe it's not a flag, maybe it's actual part of the config when defining a cluster. You can tell it specifically which network bridge you want to use instead of the default one. And then if you just bring up the worker machines using libvirt, using that same network bridge, then you have direct L2 connectivity between those two things. So it'll work in that case.
Yeah. All right. Well, I think we'll leave it there. We've been going for 2 hours. It's quite a long episode, this one. So thanks for everyone sticking around, and join us in, I don't know when we're doing the next episode. It'll be on Twitter. You'll definitely see it from Joe's account and the VMware Cloud Native apps. Click on the subscribe button and click on the bell to get reminders. Don't let the YouTube algorithm figure out if you're interested or not. Subscribe to all of the episodes. Just yours. I am not on Patreon, so don't subscribe there. Thanks everyone. We'll see you soon. Thank you so much, Jason, for spending your time with us today.
Thank you for having me. It's been fun.
Thanks. Bye.